Hello everyone and welcome to Applied Electromagnetics. Apologies for today's problems. We will post recorded lectures and stay in touch, and if the system on our e-learning page starts working back, then we might consider using it for live classes. So last class we started looking at the electric potential, and the picture that we had was that we had a charge Q moving in a path across an electric field E. So we calculated from physics the work required to move this charge, and we started looking at a couple of relationships that clarify what's going on. An important result that we reached was the potential difference taken from A to B equal to negative of the line integral of the electric field from A to B. We noticed that maintaining the negative sign allows us to have relatively consistent calculations as we try to find the potential difference from A to B, substituting for E, we get a positive value. Notice that Q here is not the charge that we're moving anymore, but rather the charge causing the electric field, and that we're moving regardless of charges from A to B. So if we have a system of point charges, then we utilize superposition in this way, and we are capable of expanding the number of charges using the known integral. An extremely important result that we came up with last class was that the negative of the gradient of the potential, remember the potential is a scalar field, equals the electric field, which is again a vector field. So we started looking at an example where we calculate the potential and the electric field at a point 0, 0, z for a circular disk with a uniform surface charge density. So here we have our disk, and we've located things conveniently such that our observation point is at 0, 0, and z. So as we start finding V, we substitute with the formula, and we chose this format since we're starting with our surface charge density. So what do I need to get to calculate this formula? I need to find my surface differential, right? So my surface differential for in this case will be rho d phi, since my normal in this case is pointing towards the positive z. And don't forget that we utilize our primes or dashes since we're talking about something that has a charge density that causes the electric field. And as we move on, like we saw last time, we found R, and then we substitute things and eventually get a formula for the potential. Okay, so now we are capable of finding the electric field in a third way. Remember, we saw first the regular analytical way from the definition of the electric field, and then we utilized Gauss's law and utilized symmetry in systems. This is a third way to find electric fields. So as we've already found our potential, we are capable of simply taking its gradient, negating it, and finding our electric field. So if we went on and did exactly that, we'll end up with this format. So only one component, and in this case, in our specific case, we have z to be positive. Then we should have this format. Remember that we said that we put z in a absolute value, since the potential should not care about direction, and having it over there, the potential should be the same as having it as in the negative side, since the potential is a scalar field again. So what about the electric field? The electric field, of course, is a vector field. And so we expand this into these two cases, where since z is greater than 0, we utilize the positive z value when z is greater than 0, and we utilize negative z when z is less than 0, of course. So that's why we end up getting these two conditions. Okay, so eventually, if we use the old definition that we had early in this chapter, we should get the same answer. So now, some points to keep in mind. We need to be careful when using our formula to find the electric field from the potential. So what do we do as we find the potential originally? We need to obtain it at a general point. And so that's when we are capable of using the electric field. So choosing this point has to be an important part of your solution. So in the previous example that we saw, things worked well since we had symmetry, since the electric field was symmetric and only had a z component in this case. And moving on, we're going to see an example where that's not the case, in fact. Okay, so here's our new example. We have half a disk with the uniform or constant surface charge density. So now we have half a disk. So we have simply broken the extreme symmetry that we had a little earlier. So in this half of a disk, we have our surface charge density rho s. So if we put down our formula that we know and start substituting, we'll get a very similar expression to what we've had earlier. Notice that phi goes only up to pi, and so you're going to have 4 instead of 2 in the denominator. So if we go ahead and calculate the electric field using the formula that we've seen a little while ago, then we might fall into the mistake that we only have a z component. The issue is that if we try to find the electric field using the regular analytical way, that we will have our r vector up above, which has actually 2 components. And as we expand for the rho unit vector, then we have this expansion, and if you were to complete this solution, then you will get a 0 for x component, a non-zero or a calculated y component, and a non-zero or calculated z component, as we saw if we've taken the gradient. Okay, so we introduce here a new topic right now, the electric dipole, section 4.9. So let's describe what an electric dipole is. An electric dipole is formed when you have 2-point charges. These 2-point charges have equal magnitude but opposing signs. And we have them here as positive Q and negative Q. And the condition that we have is that the separation between these 2-point charges is small. So we have a small distance between them. All right, so this distance, d, is divided into 2 halves and situated this way. Okay, so as you notice, the dipole, as a dipole, as the combination of these 2-point charges, lies here, and that's why the r distance is from that point to your observation point, whereas r1 distance to the positive Q and r2 is the distance to the negative Q. Okay, so if we want to find the potential at our observation point, then a simple substitution yields this as a superposition. So why do we have a negative sign here? Well, it's just that we have a negative into our charge magnitude, right? That's why that term is going to have a negative Q, and taking that Q as a common factor, we move the negative into the parentheses. Okay, so where do we go from here? We go ahead and simplify our values here, our fractions, this way. Okay, now we move our attention if r is much greater than d. And what does that mean? R is much greater than d. So my observation point is way farther away from my dipole. That renders my observation point's distance from the dipole to be much greater than the distance between the dipole's duo, or the 2 charges in the dipole. So we call this a far field situation. You'll see this word popping up in communications. And the physical meaning that matters for us is that we're going to tend to see things this way. So R1 and R and R2 will seem to be parallel as an approximation. Why is that? It's because our observation point is way, way far from my dipole. Okay, so what does this approximation yield? We're going to tend to see the differences here between R1 and R2, comparing them with R. So if we look at R1 compared with R, then it's less than R by this amount. And then R in itself is less than R2 by this amount. So what are these amounts? from the definition of cosine being the adjacent divided by the hypotenuse, then the hypotenuse in this case being d over 2, and what we're calculating here is the adjacent. Then in this case we subtract, and in this case we add by a term of d over 2 cosine of this angle, which again we approximate as equal to this angle and this angle. Okay, so now we go ahead and find the difference between R2 and R1 and write down the fact that multiplying them by each other equals almost the distance R squared, and then substituting from here using these two guys, we end up with this term. Okay, so when does this term apply? Only and if only you are in the far field, meaning your observation point is way far away, and that is in comparison to the dipole distance, or the distance between the two charges. So notice that what we've done here is really find another expression and compare this expression with this expression. So this is for a dipole in far field again. So what if we want to utilize this to find the electric field? Then in this case, symmetry in this system allows us to find negative of the gradient, and so the electric field ends up with this term. How does this term come up? It is simply because we're taking the gradient in the spherical system. So be really careful that in this case R is the radius in the spherical coordinate system, and that, looking back, that's what these are, a radius of a sphere, in the sense that the observation point can be moved anywhere on a sphere, on an equipotential sphere in that case. Okay, so we move on and say that we want to define something called the electric dipole moment as P vector equals to Q times the D vector. The D vector being the distance. So what is this distance again? It's from the negative Q charge to the positive Q charge. And if we want to write down the P vector again, then it equals the charge magnitude times the distance as a scalar into the, in this case, K unit vector, since from minus Q to positive Q, we're moving in the direction of positive K unit vector. Okay, so if I want to substitute things, I'm going to go ahead and say that QD cosine theta equals the dot product between this P vector with the R unit vector. And so the theta angle is between the D vector and the R unit vector. Okay, so now substituting all of this, we modify E from this format to this format, and we end up getting simply this formula. So just substituting QD with P. Okay, so we move on to another topic. So here we talk about energy density in electrostatic fields. So here's the scenario that we're introducing right now. We bring a charge Q2 against an electric field produced by Q1. So we have two charges. Q1 produces the electric field, and we bring Q2 against that electric field. And so in bringing Q2 against that electric field produced by Q1, work is being done. So how do we calculate work in this case? We utilize the line integral of the force vector field that we've seen in the electric potential section, and in this case we will have, as we substitute, Q2 and Q1. So what is this equal? It is equal to the value of Q2 times the absolute potential at the position of Q2 due to Q1. Okay, what if we bring Q1 in the presence of Q2? So assuming that Q2 now is the generator of the electric field. Now if we bring Q1, we end up getting this for the work. Notice that in this case we've maintained R21 as it is the magnitude of the distance between these two charges, and that did not change. So what did we do here? We just changed our perspective. Since we have Q2 and Q1 only with possibly different charge values, then we're trying to look at if we move one or the other with the other, causing an electric field to be there, then what work do we have to induce? Okay, so if we notice that these two quantities, they would be the exact same. So this is equal to this. So W21 is equal to W12. And if we maintain that they might have two formats and add them together, then we add this guy with this guy here. Dividing both sides by 2, we get this formula here. And this is the way that we tend to calculate the total electric energy. Okay? So now, suppose that we actually bring a third charge. Then there's an additional work over and beyond the work done to bring one of the charges, right? Okay, so that additional work or change in this in the work done in general is going to be equal to these two terms. So why two terms? It's because there's gonna be work due to bringing this third charge because of the electric field induced by the other two. And so that's what we have here. So going on to calculate the total electric energy, now we have three terms. And we expand these three terms. And so if we write our total electric energy with these, so we're just basically flipping these indices, as we know that these two are now equivalent. We expand this other way to represent the total electric energy this way. And so if we go ahead and add both of these, we end up having these terms. So just like what we did with two charges, we can generalize things into this rule right here. So we need to note that this expression equals the absolute potential V at Q1 due to Q2 and Q3. So an absolute potential at a specific charge due to all the other charges is represented as V of that charge and other charges. The combination of these possible potentials or absolute potentials. Okay, so this is a very important rule that we've reached, in the sense that this is how we measure energy in an electrostatic field. So as we've seen, Vi here is the absolute potential at the position of the ith charge or point charge due to all other charges. And We is the potential energy of n point charges, or work done to assemble the n charges. Okay, so remembering that we can substitute the potential as this sort of superposition, then we move on to see that for charge distributions, the total electric or electrostatic energy is equal to this quantity. So remember where this comes from. This will simply come from here. Okay, so for charge distributions we have this format where V is the potential at the position of the volume charge distribution, and V is the volume where that charge distribution exists. Okay, what if I have a surface charge distribution? I use this format. And what if I have a line charge distribution? Then I use this format. So remembering that we have this from Gauss's law, then utilizing this after a couple of steps, as the book states, we have this formula to calculate the total electrostatic energy. And if we substitute for the flux density, then we can end up with this format of this formula. Okay, so again, what is WE? In this case, it represents the energy stored in the electric field within a region with a volume of V. Okay, so let's go ahead and define lowercase we, the work on electric charges, as half of the dot product of the flux density into the electric field. Then we can go ahead and represent uppercase We, the energy stored, as basically this integral. So what do we call this, the lowercase we? In this case, it's basically a density, an electrostatic energy density. Okay, let's take this example here. What we have is a sphere of a uniform charge density, so a constant charge density, with a radius of b. And what we need to do is calculate the total electrostatic or total electric energy. Okay, so again, what we're going to utilize is going to be actually this formula here. So this is a constant, and so it can go out of the integral. And what about this? So this is what I need to actually find. And so how do I find my absolute potential? I'll utilize the negative of the line integral of the electric field. So the key word here is the electric field, and that's what we need to find. So how did we find these electric fields? By utilizing Gauss's law. Why did we use Gauss's law? Because of the symmetry that's apparent in this system. It's a simple sphere with a uniform rho v. Notice that we're looking first at the electric field when we're inside of the sphere, and we get this expression. And as we start leaving the sphere, then the enclosed charge is only that that's produced by the sphere. Okay, so we found our electric field everywhere. Where do we move from here? We calculate our absolute potential, and that notice that it contains two terms coming from both of these possibilities of the electric field, with the first term limits being from infinity to b, and the other term from b to r. So r can be outside or inside of the sphere. So in the case that it is inside of the sphere, then this expression equals this value. Okay, so moving on, we want to write down our expression for the total energy, total electrostatic energy, and we write down the expression in terms of a volume charge density and the absolute potential, of course. So we expand our volume differential for our sphere, and then go ahead and calculate our total work to be equal to this quantity. So if we utilize the other formula, it should end up giving us the same answer. So you might want to go ahead and do that, see if the other way is shorter, as in this case you might not worry about finding your absolute potential, but start thinking of how you're gonna get the absolute value or the magnitude of an electric field. Okay, so that's it for today. This way we have concluded chapter 4. Today we've taken a couple of topics. We finished looking at the electric potential. We introduced the electric dipole, and then we started looking at really energy calculations. I will post a homework today to be due 1 week from now, and it will include questions that will get you going on this final part of chapter 4, the material after the midterm. So that will be posted today, and I would like to ask you guys to choose a way that we can I can get your questions in a very easy way. So if you'd like to Skype, if you'd like to utilize another phone or a teleconference app, or if you'd like WhatsApp or simple phone calls, in the sense that office hours can extend from perhaps 9 to 4, 5 days a week that way. You can call anytime or send a message via one of the ways that I mentioned, or one way that you might suggest. So that'll be in a poll in our e-learning page. So I'd like to hear from you guys. All right, so these lectures will be dense in this sense, so utilize rewind and go ahead and resolve everything. Try to finish up the issues that we've skipped, where we asked you to derive, where we asked you to solve. And if you'd like any more examples on any topic in specific or in general, just let me know. Thank you.